Hi everyone. This presentation explores the statistical analysis of data concerning electric vehicles. This is the agenda for this presentation. From a business perspective, this project's requirement is to analyze and describe data that supports how the development of electric vehicles has contributed to the future of transportation. According to the U.S. Department of Energy, an electric vehicle is defined as a vehicle that can be powered by an electric motor that draws electricity from a battery and is capable of being charged from an external source. As a result, I decided to analyze the electric vehicle title and registration activity dataset from the Washington State Department of Licensing, which includes Washington's vehicle titling and registration records, vehicle fuel type, VIN, make, model year, electric range, location data, and historical sales data, among other associated data. According to Edmunds Editors, when calculating the number of miles an electric vehicle should have, since the typical driver has a daily commute of 30 miles round trip, the driver is recommended to multiply this typical daily commute by 3. Therefore, for an electric vehicle, the recommendation is to find a vehicle that has at least 90 miles of range. The research question I've decided to analyze states, given that Edmunds Editors recommends that the typical daily commute for electric vehicles should be equal to at least 90 miles of range, do the electric vehicles listed in the dataset match the requested recommendation? To support this research question, I used JMP to analyze mean and median as measures of central tendency, which contributed to the distribution of the data. I found that the average number for electric range for the EVs was calculated as 96.47 miles, and the median was 73 miles under the summary statistics section, which could indicate a skewed distribution. Calculating the mode was inconclusive as a limitation in data collection because, according to the Washington State Department of Licensing, 0 will be entered where the electric range has not been researched, and many data points were identified as having a value of 0. Using a histogram, I found that this data illustrated a positively skewed distribution because the tail on the right end of the chart is longer than the data on the left end. Potential outliers include the electric vehicles with electric ranges consisting of 200 to 220 miles and 220 to 240 miles because most of the EVs in the dataset have miles of range below 100 miles. Considering the distribution and overall usage, the average electric range value does adequately represent the dataset because the histogram illustrates the number of vehicles, the miles of range from 0 miles to 337 miles, and the decrease in values as the distribution moves to the right in the histogram, apart from the outliers in the 200 to 240 mile range. Regarding the nature of the electric range variable, I can conclude that electric range is typically between 0 and 100 miles, which could be due to hybrid EV models that are powered by both electric motor and internal combustion engine using gasoline, diesel, etc. Considering the analysis of means, I conducted a one-sample t-test using JMP to analyze whether electric vehicles in this dataset followed the hypothesized recommendation. The null hypothesis is that the population mean is equal to 90 miles of range, while the alternative hypothesis is that the population mean is not equal to 90 miles of range. This updated figure illustrates the average, standard deviation, and the sample size in the summary statistics section. I found the difference between the sample's average and the null hypothesis value by subtracting 90 from 96.47, which gives me 6.47 miles. Further, I found the standard error value for the mean as 0.130, calculated by dividing the standard deviation by the square root of the sample size. Given these values, I was able to calculate the test statistic by dividing the difference between the sample's average and null hypothesis value by the standard error value for the mean, which equaled 49.81. Then, looking at a t-table referencing the significance level of 0.05 and associated degrees of freedom, I was able to find the critical value of t as 1.96. According to the figure, given a significance level of 0.05, degrees of freedom as 545,227, a left-tailed p-value of 0.0001, and because the test statistic is greater than the critical value of t, I am 95% confident that I can reject the null hypothesis that the population mean is equal to 90 miles of range. The typical electric vehicle does not have exactly 90 miles of range, but rather more or less miles of range. Considering the statistical significance of the model, I was able to conduct a bivariate regression analysis for the electric range by model year, consisting of a fit line, p-value, and an r-squared value. The fit line illustrates whether there is a trend or correlation between the dependent and independent variables. The p-value describes the strength of the relationship between these two variables, and the r-squared value describes the extent to which the variance of one variable explains the variance of the second variable. Since the data is positively skewed, the fit line does not necessarily provide a reliable representation of the correlation between the analyzed variables. However, the p-value of 0.0001 indicates that there is a statistically significant relationship between electric range and model year. Regarding how the variance of the model year explains the variance of the electric range, the r-squared value means that approximately 0.03 of the observed electric range data is slightly affected by the difference in model year. The figure illustrates that as EVs progress over time, the electric range capability more than likely increases due to advances in technology and companies competing for the best EV business. Taking correlation and causation into account, specifically in 2017 and 2018, EVs with electric range greater than or equal to 90 miles began to gain popularity. For example, in this dataset, the 2017 Ford Focus had an electric range equal to 100 miles. However, correlation does not imply causation. In 2018, the Kia Soul EV had an electric range equal to 111 miles, while the Fiat 500 had an electric range equal to 84 miles, and the Smart EQ42 had an electric range equal to 58 miles. These examples explain why the model year does not cause electric vehicles to have a typical electric range of 90 miles or greater based on correlation. Following data analysis, I found 3 significant data limitations and biases to discuss. Although the Washington State Department of Licensing suggests that from March 2020 to February 2021, numbers were lower due to the COVID-19 pandemic, an example of omitted variable bias associated with data collection for this dataset could include employment status for each driver and their respective vehicle. For example, in conjunction with the earlier statement, working from home since the start of the pandemic has increased, meaning that people do not drive every day compared to working in person. Further, some people are unemployed, stay-at-home parents, and/or retired, which means that driving habits are different for the 545,228 values listed in the dataset. As a result, the hypothesized mean of 90 miles of range might need to change given the new circumstances of people driving different distances, which might change the results. Another potential example of omitted variable bias could include people who registered their vehicles in a single documented year and have since moved from Washington, and those who have recently moved to Washington with an electric vehicle but have not registered and titled their vehicles for some reason. While not necessarily a significant value, this hypothetical bias could be more significant if there are more people that have not changed their status, or if the system that tracks these statuses has not been updated since 2010 when data collection began. A third example of omitted variable bias includes electric range data, identified as the value 0, that has not been researched or updated in the dataset. This bias affects and skews the data and overall results of the analysis. Had these incomplete data been updated or researched, the missing values could have been filled by other ranges, contributing to the sample's average and associated metrics. In conclusion, using JMP, I analyzed the electric vehicle title and registration activity dataset from the Washington State Department of Licensing to examine whether the electric range variable of electric vehicles match Edmunds Editors' recommendation to have at least 90 miles of range for a typical daily commute. Applying descriptive statistics, I found that the average typical range for EVs was 96.47 miles, even though the data illustrated a positively skewed distribution, implying that most of the electric range data is typically between 0 and 100 miles. Further, I conducted a one-sample t-test using JMP to analyze the hypothesized recommendation, of which the null hypothesis was that the population mean is equal to 90 miles of range, while the alternative hypothesis was that the population mean is not equal to 90 miles of range. I found that given a significance level of 0.05, degrees of freedom as 545,227, a left-tailed p-value of 0.0001, and because the test statistic is greater than the critical value of t, I am 95% confident that I can reject the null hypothesis that the population mean is equal to 90 miles of range. The typical vehicle does not have exactly 90 miles of range, but rather more or less miles of range. Finally, I conducted a bivariate regression analysis of which the p-value indicated a statistically significant relationship between electric range and model year. However, the r-squared value of 0.03 indicated minimal change due to the model year, and that the model year does not affect EV's electric range based on correlation. I appreciate your time and I look forward to your responses.